please hit subscribe.
Here we discuss the easiest type of differential equation that can be solved, that is the variable separable differential equation. The form of this easiest type of differential equation is as follows. We have a derivative, then here we have a function of one of the variables, in this case x, and another function of the other variable. We can also write it in the following manner, where we just replace the derivative with y prime, and also we can write it in the differential form like this way. And we will notice that the function of one variable and the function of the other variable are separated. That means they are factors of this expression here, and that is what we mean by variable separable, that we can separate into factors the expression that contains one variable and the other expression that contains the other variable. And also another feature is that we can write the derivative alone in one of the sides. So in this case it's on the left side. And again on the right side here we have the product of two functions, each function containing only one variable. Now let's look at some examples of variable separable differential equations. So here we have y prime equals ay. We can factor this out into f of x equals the constant a and g of y equals y. So it now looks like this form. And when we say that it looks like this form, it doesn't mean that there is only one way of expressing f of x. There could be several ways. For example, we can have f of x equals 1 and g of y equals ay. So that's still a valid decomposition. What we mean here is that there is some decomposition where the x's are in one factor and the y's are in another factor. Now the next example is this one, x prime equals x squared. The independent variable here is t and the dependent variable is y. Now we can take f of t equals 1 and g of x equals x squared. The third example is x prime equals tx, and this is rather simple. F of t equals t and g of x equals x. So again we are able to separate the x's from the t's. Then here we have a slightly different example. We have y prime plus a of x, y equals 0. Now we want the derivative to be on one side, so if we do some algebra we can put it into this form. Y prime equals minus a of x, y. Now we can separate this expression into f of x, where in this case we choose f of x equals minus a of x, and y would be our g of y. So again, this is, even if it looks like this is still a variable separable differential equation, because we can express it in this way, where on one side there's the derivative and on the other side is a product of two functions, one function of x's and the other function of y's. Then here we have the last example is y prime equals 1 minus y squared. Here we choose f of x equals 1 and g of y equals 1 minus y squared. We just know to ourselves that the operation between f of x and g of y must be multiplication. It cannot be addition or subtraction, and therefore we cannot have g of y equals y squared and g of x equals, or rather f of x equals 1. We cannot have that because that is gonna be separated by addition or subtraction. So 1 minus y squared must come together. It's one factor, and f of x must be a constant in this case. So let us try to solve this differential equation, which was an example in the previous slide. And the first thing we notice is that the simplest case is when y equals 0. So we are asked is y equals 0, identically 0, a solution to this differential equation? In fact, if y equals 0, then the derivative dy dx is just 0, and therefore y prime equals 0. That means y equals 0 is a solution to this differential equation, because when you substitute y equals 0 to this equation, you get an equation again. So that means this is a solution. Now, for the case when y is not 0, what we can do is divide both sides by y. And we can do that because y is not 0. And now looking at this equation, we can say that maybe we can just integrate both sides. Here we integrate with respect to y, and here we integrate with respect to x. And we get the definite integral, and they should be equal. In this case, we have a constant x sub 0, and x is the variable here. And then we define another constant y sub 0 to be the value of y at x sub 0, and y is just the value of y at x. And we know how to do the integral on the left and on the right. And so let's just do that with some algebra. Now here, let's just combine the constants here to C1. And then let's just get the inverse of this logarithm, and we are now able to extract y of x. And we note here that the constant c sub 2 is actually the constant e raised to the c sub 1, and therefore this can never be equal to 0. So the exponential doesn't equal to 0 for any value of c sub 1. And at the same time, we have the plus and minus sign here because this used to be an absolute value symbol. There used to be an absolute value symbol here. So now that plus minus and the absolute value symbol is subsumed in c sub 2. Now we can say that the solutions to this differential equation are y equals 0 and y equals c sub 2 e to the ax, where c sub 2 is not 0. However, we can see that we can actually think of this first solution as a constant c sub 2, where c sub 2 equals 0. And therefore, we can just abbreviate the solution into just one statement, saying that y equals c e raised to the ax, and in this case c is any real number, including 0, because if we substitute 0 here, then we obtain this solution. This way of solving this differential equation may seem very appealing and convincing. However, there is one weakness. This bit here, we said that perhaps when we do the definite integral on the left side, it should be equal to the definite integral on the right side. However, that is not necessarily true because we have a dy here and we have a dx here. They're not the same variables, and so operating on different variables, doing the integration operation on both sides with different variables does not necessarily mean that they have to be equal. And in fact, we are never taught that in calculus. So in calculus, we only learn to compute one side. So we learned how to compute this integral, and we learned how to compute this integral, but we are never told that they should be equal. And so in the next slides, we will show that in fact, they will be equal in the sense that we are using them here. So let's begin by trying to compute the general solution of this differential equation, this variable separable differential equation. So again, let's start with the case when g of y equals 0. If g of y equals 0, then this whole expression on the right equals 0. It becomes like this. The solution to this is simply y of x equals some constant. So any constant here when we substitute that here, that will yield us a derivative of 0. And therefore this derivative becomes 0, and this side is also 0. And therefore, we can say that y equals c sub 0 is a solution to this differential equation. Now for the case when y is not 0, or rather when g of y is not 0, we can now divide both sides of this equation by g of y. And we obtain this. Now, both expressions are in terms of x. So this is a function of x, and this is also a function of x. So now what we can do is actually get the definite integral of both sides with respect to the same variable x. And here, that's what we do. We have the same variable of integration, x, and the same limits of integration. Now, this is unquestionably equal because we are doing the same operation on both sides. Now, the difference between this and that of the previous slide is that in the previous slide, we had y here and we had x here. So it is arguably a different operation on the left side and on the right side. But in this case, it's exactly the same operation, and so the equality symbol is unquestionable. Now we do the substitution u equals y, and if we do that, we have the following differential, du equals dy dx dx. And we have y sub 0 equals u of x sub 0 equals y of x sub 0. And if we use these substitutions, we obtain the following. Now it's much simpler. And here we notice that we have a variable, a constant, and a constant. And what we will get is an expression with two variables and two constants. So what we can do is we can actually collapse the constants into just one constant, and we will be left with the variables. And that's really the same as doing the indefinite integral. And so we can just express this in terms of indefinite integrals. So it will be like this. And therefore, the solutions to this variable separable equation is actually this and this. So we just have to get here the indefinite integrals and solve for y. In this video, we learned about the easiest kind of differential equation, and that's the variable separable differential equation. We call it variable separable because we can factor out the x's and the y's. In other words, we can separate them into factors. And this equation is often written in the following forms. This first form has this derivative here. Then we have a function of x and a function of just y. Then we can replace this derivative with this symbol, or we can also replace it with the differential symbol here. And we learned that the solution to this variable separable differential equation, the solutions are as follows. So if g of y equals 0, then we have a solution that is in the form y equals some constant. So this is the constant solution. And when g of y is not 0, then the solution is such that we get the antiderivatives of both sides of this equation, and we just solve for y explicitly. And just to give ourselves a little more practice on this, we invite you to actually answer the following challenges. So here are variable separable differential equations, and I invite you to give them a go. So here we are just asked for general solutions, and here we are asked for particular solutions. So you can review the videos we had about particular and general solutions to have an idea of how to solve them. And then I'm also putting a link to videos here on examples on actually trying to impose the conditions to obtain the particular solution.
Please hit subscribe.